Yes, there is a potential difference between neutral and ground. Neutral is a point in an electrical system that is intentionally grounded for safety reasons. It is usually connected to the center tap of a transformer winding or to the grounded conductor of a service entrance cable. Ground is a point in an electrical system that is connected to the earth. It is typically connected to a ground rod driven into the earth or to a water pipe. The potential difference between neutral and ground is typically small, usually less than 1 volt. However, it can be higher in some cases, such as when there is a fault in the electrical system. Yes, there is a balance that is needed between neutral and ground in order for the service to operate effectively. If the neutral is not properly grounded, the voltage on the neutral can fluctuate, which can cause problems with sensitive electronic equipment. If the ground is not properly connected, the system may not be able to clear fault currents quickly enough, which can lead to a fire or shock hazard. Yes, it is true that if there is no ground at all to the ground rod or water pipe, the system will act funny. Without a proper ground, the system will not be able to clear fault currents properly, which can lead to a fire or shock hazard. Additionally, the voltage on the neutral can fluctuate, which can cause problems with sensitive electronic equipment. The debate over grounding stems from the fact that some people believe that grounding is not necessary for safety. However, the vast majority of electrical experts agree that grounding is essential for safety. Grounding provides a low resistance path for fault currents to flow, which prevents them from flowing through people or equipment. We have figured out the importance of grounding. Grounding is an essential safety feature that is required by all electrical codes. It is important to make sure that the electrical system is properly grounded in order to protect yourself and your property. Grounding is a critical safety measure in electrical systems, and understanding its principles and proper implementation is vital for ensuring safety and preventing electrical hazards. Here's a detailed explanation of grounding, its importance, and how it functions. Firstly, the purpose of grounding is to provide a low impedance path for fault currents to return to the source, typically the transformer. This low impedance path facilitates the rapid tripping of overcurrent protection devices, such as circuit breakers or fuses, in the event of a fault. Fault is an unintentional electrical connection between a live conductor and a grounded surface or equipment. Without a proper grounding system, fault currents may not be sufficient to trip these protective devices, leading to prolonged exposure to dangerous voltages and potentially causing electrical shock, fire, or equipment damage. Secondly, grounding helps to stabilize voltage levels in the electrical system. By providing a reference point connected to the earth, grounding minimizes voltage fluctuations and prevents the buildup of static electricity. This is particularly important for sensitive electronic equipment, which can be damaged or malfunction due to voltage variations or electrostatic discharge. Thirdly, grounding minimizes the risk of electrical shock. When a fault occurs, the grounded metal parts of equipment and appliances become energized. A properly grounded system ensures that these parts are at or near ground potential, so if a person comes into contact with them, the voltage difference is minimal, reducing the likelihood of a dangerous electrical shock. There are two main types of grounding systems: equipment grounding and system grounding. Equipment grounding involves connecting the non-current carrying metal parts of electrical equipment, such as enclosures, conduit, and motor frames, to the grounding electrode system. This provides a low impedance path for fault currents to flow back to the source, tripping the overcurrent protection device and energizing the faulty equipment. System grounding, on the other hand, involves grounding one of the current carrying conductors of the electrical system, typically the neutral conductor. This establishes a reference point for the voltage in the system and helps to stabilize voltage levels. In a typical residential or commercial electrical system, the neutral conductor is grounded at the service entrance, where the power enters the building. The grounding electrode system consists of one or more grounding electrodes that are connected to the earth. Common types of grounding electrodes include ground rods, metal water pipes, and ground rings. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a depth of at least 8 feet. Metal water pipes can also be used as grounding electrodes, but they must be in direct contact with the earth for at least 10 feet. Ground rings are continuous conductors that are buried in the earth around the perimeter of a building. The size and type of grounding electrode required depends on the size of the electrical system and the local soil conditions. The National Electrical Code (NEC) provides detailed requirements for grounding electrode systems, including the minimum size of grounding conductors and the methods for installing grounding electrodes. Grounding conductors are used to connect the equipment grounding system and the system grounding conductor to the grounding electrode system. These conductors must be sized according to the NEC and must be protected from physical damage. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. Grounding is not a substitute for overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Grounding works in conjunction with overcurrent protection to provide a comprehensive safety system. When a fault occurs, the grounding system provides a low impedance path for the fault current to flow back to the source, which causes the overcurrent protection device to trip and de-energize the circuit. Without both grounding and overcurrent protection, electrical systems would be much more dangerous. Improper grounding can have serious consequences, including increased risk of electrical shock, fire, and equipment damage. Common grounding mistakes include using undersized grounding conductors, failing to properly bond metal parts, and neglecting to maintain the grounding system. It is essential to follow the NEC and local electrical codes when installing and maintaining grounding systems. Regular inspections of the grounding system can help to identify and correct potential problems before they become hazards. These inspections should include checking the condition of grounding conductors, grounding electrodes, and bonding connections. Grounding is a complex and critical aspect of electrical safety. Understanding the principles of grounding, the types of grounding systems, and the requirements of the NEC is essential for ensuring the safety and reliability of electrical systems. By properly grounding electrical systems, electrical shock hazards can be minimized, the risk of fire can be reduced, and sensitive electronic equipment can be protected from damage. Always consult with a qualified electrician when working on electrical systems to ensure that all work is performed in accordance with the NEC and local electrical codes. The NEC provides specific guidelines for grounding and bonding, which are essential for maintaining a safe electrical system. One important aspect of grounding is bonding, which involves connecting all metal parts of the electrical system together to create a common ground. This includes metal conduits, enclosures, and equipment frames. Bonding ensures that all metal parts are of the same potential, minimizing the risk of electrical shock. The NEC specifies the methods and materials that must be used for bonding, including the use of bonding jumpers and grounding bushings. Bonding jumpers are used to connect metal parts that are not directly connected to each other, while grounding bushings are used to provide a secure connection between metal conduit and equipment enclosures. Another important aspect of grounding is the grounding electrode system, which is the means by which the electrical system is connected to the earth. The NEC recognizes several types of grounding electrodes, including ground rods, metal water pipes, and concrete encased electrodes. Ground rods must be at least 8 feet long and must be driven into the earth to a depth of at least 8 feet. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet and if they are electrically continuous. Concrete encased electrodes, also known as UFO grounds, are installed in the concrete foundation of a building and provide a very effective grounding system. The NEC also specifies the size and type of grounding conductors that must be used to connect the grounding electrode system to the electrical system. Grounding conductors must be sized according to the size of the overcurrent protection device protecting the circuit and must be protected from physical damage. In addition to the general grounding requirements, the NEC also includes specific requirements for grounding different types of equipment and systems. For example, there are specific requirements for grounding swimming pools, spas, and hot tubs, as well as for grounding sensitive electronic equipment. These specific requirements are designed to address the unique hazards associated with these types of equipment and systems. Grounding is a critical safety measure that is required by the NEC. By following the NEC guidelines for grounding and bonding, electrical systems can be made safer and more reliable. It is important to consult with a qualified electrician when working on electrical systems to ensure that all work is performed in accordance with the NEC and local electrical codes. Proper grounding ensures that fault currents have a low impedance path to return to the source, which helps to quickly trip over current protection devices and prevent electrical shock hazards. The debate over grounding often arises due to misunderstandings about its purpose and function. Some individuals may believe that grounding is unnecessary or that it is only required for certain types of equipment or systems. However, the vast majority of electrical experts agree that grounding is essential for safety and that it should be implemented in all electrical systems. One of the main reasons for the debate is the fact that grounding is not always visible or easily understood. Unlike other safety measures, such as circuit breakers and fuses, grounding is often hidden behind walls or buried underground. This can make it difficult for people to appreciate its importance and to understand how it works. Another reason for the debate is the fact that grounding requirements can be complex and confusing. The NEC includes detailed guidelines for grounding and bonding, but these guidelines can be difficult to interpret and apply. This can lead to confusion and disagreement among electricians and other professionals. Despite the debate, the importance of grounding is well established and supported by scientific evidence. Studies have shown that proper grounding can significantly reduce the risk of electrical shock, fire, and equipment damage. For example, a study by the National Institute of Standards and Technology, NIST, found that grounding can reduce the risk of electrical shock by as much as 90%. In addition to the safety benefits, grounding can also improve the performance and reliability of electrical systems. By providing a stable reference point for voltage, grounding can help to minimize voltage fluctuations and prevent damage to sensitive electronic equipment. Grounding can also reduce the amount of electromagnetic interference, (ME), in electrical systems, which can improve the performance of communication and control systems. The importance of grounding is also recognized by insurance companies and regulatory agencies. Many insurance companies require that electrical systems be properly grounded in order to be covered by insurance policies. Regulatory agencies, such as the Occupational Safety and Health Administration, OSHA, also require that employers provide a safe working environment for their employees, which includes ensuring that electrical systems are properly grounded. In conclusion, the debate over grounding is largely based on misunderstandings about its purpose and function. The vast majority of electrical experts agree that grounding is essential for safety and that it should be implemented in all electrical systems. Proper grounding can significantly reduce the risk of electrical shock, fire, and equipment damage, and it can also improve the performance and reliability of electrical systems. It is important to follow the NEC guidelines for grounding and bonding and to consult with a qualified electrician when working on electrical systems. The NEC provides specific tables and examples to guide the proper sizing of grounding conductors, bonding jumpers, and grounding electrodes. These tables take into account the size of the overcurrent protection device, the type of equipment being grounded, and the type of grounding electrode being used. For example, NEC Table 250.122 provides the minimum size of equipment grounding conductors for grounding raceway and equipment. This table specifies the minimum size of the grounding conductor base and the rating of the overcurrent protection device protecting the circuit. Similarly, NEC Table 250.66 provides the minimum size of grounding electrode conductors for connecting the grounding electrode to the electrical system. This table specifies the minimum size of the grounding electrode conductor base and the size of the service entrance conductors. In addition to the tables, the NEC also provides examples of how to properly ground different types of equipment and systems. These examples illustrate the correct methods for connecting grounding conductors, bonding jumpers, and grounding electrodes. For example, the NEC provides examples of how to properly ground swimming pools, spas, and hot tubs, as well as how to ground sensitive electronic equipment. It is important to carefully review the NEC tables and examples to ensure that electrical systems are properly grounded. Failure to follow the NEC guidelines can result in electrical shock hazards, fires, and equipment damage. Grounding is a complex and critical aspect of electrical safety, and it is essential to have a thorough understanding of the NEC requirements. Grounding serves as a crucial component in electrical safety by providing a low-impedance path for fault currents. This path allows for the rapid tripping of overcurrent protection devices, such as circuit breakers and fuses, effectively minimizing the risk of electrical shock and fire hazards. By connecting non-current carrying metal parts of electrical equipment and systems to the earth, grounding ensures that these parts remain at or near ground potential. This prevents dangerous voltage build-up and reduces the likelihood of electrical shock if a person comes into contact with them. In addition to its role in safety, grounding also contributes to the reliable operation of electrical systems. By providing a stable reference point for voltage, grounding helps to minimize voltage fluctuations and prevent damage to sensitive electronic equipment. This is particularly important in modern homes and businesses that rely on computers, communication systems, and other electronic devices. Grounding is not a one-size-fits-all solution. Different types of electrical systems require different grounding methods and techniques. For example, a residential electrical system will typically have a different grounding configuration than an industrial electrical system. The NEC recognizes these differences and provides specific guidelines for grounding different types of systems. In addition to the NEC, local electrical codes may also have specific requirements for grounding. These local codes may be more stringent than the NEC requirements and must be followed to ensure compliance. It is important to consult with a qualified electrician to determine the appropriate grounding methods and techniques for a particular electrical system. A qualified electrician will have the knowledge and experience to properly design and install a grounding system that meets the NEC and local code requirements. Grounding is not a static concept. As technology advances and electrical systems become more complex, grounding requirements and techniques may change. It is important to stay up to date on the latest grounding practices and to ensure that electrical systems are grounded in accordance with the current standards. The NEC is updated every 3 years to reflect the latest advancements in electrical technology and safety practices. Staying informed about these updates is crucial for maintaining safe and reliable electrical systems. Grounding is an essential element of electrical safety that should not be overlooked. By providing a low impedance path for fault currents and stabilizing voltage levels, grounding helps to protect people and equipment from electrical hazards. It is important to follow the NEC and local electrical codes when installing and maintaining grounding systems and to consult with a qualified electrician when necessary. Grounding is a fundamental aspect of electrical engineering that plays a critical role in ensuring the safety and reliability of electrical systems. Its primary function is to provide a low impedance path for fault currents, allowing them to quickly return to the source and trip over current protection devices, such as circuit breakers and fuses. This rapid response minimizes the risk of electrical shock and fire hazards. Grounding also helps to stabilize voltage levels within the electrical system, preventing voltage fluctuations and protecting sensitive electronic equipment from damage. Without proper grounding, electrical systems can become dangerous and unreliable. There are two main types of grounding: equipment grounding and system grounding. Equipment grounding involves connecting the non-current carrying metal parts of electrical equipment to the grounding electrode system. This creates a low impedance path for fault currents, ensuring that the metal parts remain at or near ground potential. System grounding, on the other hand, involves grounding one of the current carrying conductors of the electrical system, typically the neutral conductor. This establishes a reference point for the voltage in the system and helps to stabilize voltage levels. The grounding electrode system is the means by which the electrical system is connected to the earth. It typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. The grounding electrodes must be properly sized and installed to ensure that they provide a low impedance connection to the earth. The NEC provides detailed requirements for grounding electrode systems, including the minimum size of grounding conductors and the methods for installing grounding electrodes. Grounding conductors are used to connect the equipment grounding system and the system grounding conductor to the grounding electrode system. These conductors must be sized according to the NEC and must be protected from physical damage. Improper grounding can have serious consequences, including increased risk of electrical shock, fire, and equipment damage. Common grounding mistakes include using undersized grounding conductors, failing to properly bond metal parts, and neglecting to maintain the grounding system. It is essential to follow the NEC and local electrical codes when installing and maintaining grounding systems. Regular inspections of the grounding system can help to identify and correct potential problems before they become hazards. Grounding is a complex and critical aspect of electrical safety. Understanding the principles of grounding, the types of grounding systems, and the requirements of the NEC is essential for ensuring the safety and reliability of electrical systems. By properly grounding electrical systems, electrical shock hazards can be minimized, the risk of fire can be reduced, and sensitive electronic equipment can be protected from damage. Always consult with a qualified electrician when working on electrical systems to ensure that all work is performed in accordance with the NEC and local electrical codes.